طيب. So let us talk about how we add bits. Okay, so let us see how we add bits in binary. Where is? Okay, here we go. So first, I'm going to show you how we can do addition in binary. I'll talk about subtraction. If I have time, I'll talk about multiplication today. Now, we know that 1 plus 1 is equal to 2 in decimal, but 2 cannot be represented in binary as a single digit. So therefore, we have to use 1, 0. So 1, 0 in binary is 2. So this means that when you add 1 plus 1, you get the sum equal to 0, and you get the carry is equal to 1. So you get 2 bits. When you are adding bits in binary, you get 2 bits. So you get a sum bit and the carry. So this is actually shown here. Okay, 0 plus 0, you get 0 and the carry. 0 plus 1, you get a 1. Okay, so you get actually 0 and the carry is 0. Here you get 1 as the sum and the carry is 0. Here you get also 1 plus 0, you get 1 and the carry is 0. Now 1 plus 1, you get the sum bit equal to 0 and you get the carry bit equal to 1. So that's 2. So we get the carry is equal to 1. Now, when you get the carry, what happens? When you get the carry? Yes, Ali?
Doctor, what does carry mean?
Well, we'll see if you are adding 2 numbers in decimal. When you add, for example, 5 plus 5, you get 10. So the sum is equal to 0 and the carry is equal to 1.
Ah, okay.
All right.
Yes.
So it's the same thing in binary. So when you get 2, you get the sum equal to 0 and you get the carry is equal to 1. So the carry is propagated to the next bit because you are adding multiple bits in binary. So for example, if I would like to add now 2 bits and there is a carry, so they become 3 bits. So let us see how we add 3 bits in binary. So we have 8 cases, 0 plus 0 plus 0, the sum equal to 0 and the carry equal to 0. So there is no carry. 0 plus 0 plus 1, you get 1. So S is equal to 1, the sum bit is equal to 1, and there is no carry. 0 plus 1 plus 0, you get 1, and there is no carry. Now 0 plus 1 plus 1, here you get 2. So the sum equal to 0, and the carry is equal to 1. So that's here is the carry, which is shown as 1. This is actually S. This is the sum bit, and this is the carry. Like, continue. So there are actually 8 cases. 1 plus 0 plus 0, you get 1, and there is no carry. 1 plus 0 plus 1, you get 2. So the sum equal to 0, and there is a carry. Carry is equal to 1 here. 1 plus 1 plus 0, the same thing. And 1 plus 1 plus 1, here you get 3. So therefore, the sum is equal to 1, and the carry is equal to 1. So this is basically how we add 3 bits vertically. Now let us do binary addition. Now suppose I would like to add 2 numbers in binary. In my example here, I'm going to show you 8 bits. So I'm going to add 8 bits plus 8 bits. So we're going to start at the least significant bit, which is the rightmost bit. So we start by adding 0 plus 1. So 0 plus 1 is equal to 1. Now, before I do the addition, let us convert each number to decimal. If you look at the first number, it is 54 in decimal. If you look at the second number, it's 29 in decimal. You can convert it from binary to decimal. This is easy. So this must be equal to 2. So this is 2 plus 4. This must be 6. Here you have 16 plus 32. If you add all of these, you get 54. So that's the decimal value. You do the same thing, you get 29 for the second number. So that's easy. You can convert each number from binary to decimal. Now we are going to add them in binary, the same way that the computer does it. So the computer adds the bits in binary. It adds the numbers in binary. So let me clear here my erase. Okay, yes. So let us start again. So 0 plus 1, what do I get? 0 plus 1?
1. And the carry
is there a carry?
No.
No.
Okay, so we write 1 and there is no carry. 1 plus 0?
1.
1. Without carry.
Okay, how about 1 plus 1?
0 and carry 1.
Exactly. I have to put the 0 and the carry. So notice that now, because we are using a carry, the carry is propagated to the next bit. That's the meaning of the carry. The same way that we do actually decimal addition, but here we are doing it easier in binary because there are only 0 and 1s. That's it. So now notice, because we have a carry, we have to add 3 bits vertically. So 1 plus 0 plus 1, what do I get?
0 and 1 carry.
0 and the carry. Notice that how the carry is propagated. So now 1 plus 1 plus 1, what do I get?
1 and carry 1.
Exactly, 1, and there is a carry. Now this carry here, which is 1, added 1 plus 1 plus 0, what do I get?
0 and 1 carry.
And 1 plus 0 plus 0?
1. Without carry.
No carry. 0 plus 0?
0.
So we have done this addition in binary. This is basically how we can design a circuit inside the computer that does this addition in binary. I'll talk about how we can design circuits later. I will show you how we can design a circuit that does specifically addition. We can actually make it to do addition. We can make a subtraction. I will talk about all of these topics in this course. Okay, so it is really interesting how you can design a circuit inside the computer that does addition. Now, let us convert this number from binary to decimal. If you look at this number here, okay, so you have 1 plus 2, here you have 16, here you have 64. If you add these bits, you get 83. Now, if you do the addition in decimal, you will also get 83. So basically, whether you do the addition in binary or you do the addition in decimal, you will get exactly the same number. But the way that the computer does it in binary. But if you would like to do it by decimal, by hand, you will get exactly the same value. So this is why, okay, I am converting the number from binary to decimal to show you that you will get exactly the same result. So that's basically binary addition. Let's talk about subtraction. Now, how do I subtract? Now, we know that in decimal, we use the concept of the borrow. I'm going to talk today about the borrow. But later I'll come back and show to you how we can use negative numbers inside the computer, how we can represent negative numbers, and we can convert subtraction into addition to the negative, okay, to the negative number. So I'll talk about how we represent negative numbers in the 2's complement representation. And once you understand how we represent negative numbers, we can convert subtraction into addition. So x minus y becomes x plus negative of y. So basically, we can convert the subtraction into addition to the negative of y, and the negative of y we represented using the 2's complement representation. I'll come back to this topic later. But first, let us understand how we do the subtraction using the concept of the borrow that already we know it, okay, from decimal subtraction. So in order to subtract x minus y, we get the difference, which is d, and we get a borrow. Now, the borrow here, I'm going to show it to you as 0 or minus 1 because we are borrowing from the next bit. So, for example, we have 4 cases here. So, according to x and y, because x and y are in binary, so we have 0 minus 0, we have 0 minus 1, we have 1 minus 0, and we have 1 minus 1. Now, 0 minus 0 is very easy. 0 minus 0 equal to 0, and there is no borrow. Now, 0 minus 1 is interesting. I cannot subtract 0 minus 1 because 0 is less than 1. So I have to borrow. So my borrow here is shown as negative 1. Okay, that's the indication of the borrow. And now, because I'm borrowing from the next bit, now I'm going to borrow a 2. In the case of decimal, the borrow is 10. In the case of binary, the borrow is 2. So therefore, this becomes actually 2 minus 1, it becomes 1. So the difference is equal to 1, and there is a borrow. Now, this is the difficult case because we have actually here x is less than y. We have 0 minus 1. In the case of 1 minus 0, it's very simple. It's just 1. There is no borrow. And 1 minus 1 is also easy. We get actually 0, and there is no borrow. Okay? So this is basically how we can subtract 2 bits. But now, if I would like to subtract multiple bits, I have to propagate the borrow. Because we are going to propagate the borrow, okay, so let us now do it, okay, with the borrow in. So I'm going to show you now x minus y, but there is a borrow, okay, on top of that. Now, when there is a borrow, I have to borrow it from the x. Okay, so I have to borrow it from the x. The same way that we do it in the case of decimal, but we are going to do it in binary. So there are actually here also, because x and y can be 0, 0, or 0, 1, 1, 0, and 1, 1. Let us take a look at these 4 cases and understand them. So if there is a borrow here, notice that I'm showing a borrow on top of the 0. Now we cannot borrow from the 0. So therefore we have to borrow again. We have to borrow again. So this borrow is propagated. And therefore, when you borrow again, this 0 becomes 2, not 10. In the case of decimal, it becomes 10. In the case of binary, it becomes 2. So now when you borrow again, this becomes 2. And when it becomes 2 minus 1, it becomes 1. And 1 minus 0 becomes 1. So this is what you get when you have a borrow in. Okay, let us take a look at this case. So there is a borrow, and here I would like to subtract 0 minus 1 with a borrow. This is a borrow in. That's actually is an input borrow. So I cannot borrow from the 0. I have to borrow again. So this 0 becomes 2. 2 minus 1 becomes 1. 1 minus 1 becomes 0. So you can see that the difference equal to 0, and I get the borrow out. So the borrow out is shown here. So let me use here my pen tool. So what is shown here on top is the borrow in, and this is actually is the borrow out, which is shown at the bottom. Let me use actually here my stylus pen. This will be actually easier and cleaner.
Doctor, the borrow out will be propagated to the next.
Exactly, the borrow out is going to be propagated. So this is my borrow in here, and this is my borrow out. Of course, my borrow out is going to be propagated to the next bits. I'm going to show you the one I actually subtract multiple bits from multiple bits. Right. All right. So you understand this concept. Let us take a look here at the remaining 2 cases. Now notice that here my borrow in is the minus 1. That's my borrow in. Okay. I can borrow it from 1. So basically this minus 1, I can borrow it from this one. So it becomes 0. So 0 minus 0 is 0, and there is no borrow out. Okay. So there is no borrow to be propagated. And finally here, I have my borrow in. I can borrow it from the 1. So it becomes 0. But 0 minus 1, I have to borrow again. Okay. So I have to borrow again. So therefore, in order to borrow again, so this 0 becomes 2. 2 minus 1 becomes 1. Okay. So this actually shows you all the 4 cases that you are going to encounter when we do subtraction. So let us take a look here at this example. Now I would like to subtract multiple bits, okay, from multiple bits. So I have these 2 numbers. Let us look at these 2 numbers in decimal. Now the first number is again 54. It's the same number that we have seen in the case of addition. And the second number is 29. Now here 54 minus 29. Well, we expect the difference to be equal to what? What's the difference? 54 minus 29 is equal to what?
25.
25.
Okay, let us see if we are going to get this result. Okay, so let us actually do the subtraction in binary. Now 0 minus 1, let us start at the least significant bit. So 0 minus 1, I cannot subtract unless I borrow, right?
Yeah, it's going to be 1.
So therefore, we have
borrow
to borrow from the next one. So let us actually show the borrow here.
So
So the borrow here is propagated to the next bit. That actually is my borrow. And now this 0 becomes actually 1, 0. It becomes 2 after borrowing, right? And 2 minus 1 is equal to 1. Hello?
Yes, yes.
Yes.
Right. So now when we borrow from this one, this becomes 0. 0 minus 0, we get 0 with no borrow. Now 1 minus 1 is 0, and there is no borrow.
Yes.
This is easy, right? Now 0 minus 1, what will happen?
1 and borrow 1.
So we have to borrow. We have to borrow, right? So there is a borrow. طيب, what will happen now?
It's going to be a borrow again.
Minus 1.
You need to borrow.
This becomes 0, right?
Yeah.
So we have to
0
borrow
minus 1 we
again.
need to borrow.
We have to borrow again. So when we borrow, it becomes 2 minus 1, we get 1, and there is a borrow. Now this becomes 0. 0 minus 0.
0.
0.
And
All
there
of
is
the
no
rest
borrow.
is 0. Yeah.
0 minus 0 is equal to 0. That's it. Now, what is this number? It is 16 plus 8 plus 1. It is 25, as we expected. As we expected. So we got 25. Now, notice that 54 is larger than 29. So for this reason, we got the result to be 25. However, if we would like to calculate 29 minus 54, try it. You will get a borrow. So if the first number is smaller than the second number and you are subtracting, then the difference will be negative. But so far, we don't know how to represent negative numbers in binary. I need to talk about this. I did not talk about this. So if you are doing it using the concept of the borrow, you will get some bits here, but these bits will not represent a positive number. They will represent a negative number. And you will get a borrow. Okay, you will get a borrow. So for this reason, I'm going to postpone this discussion till later. So you can do the subtraction in binary normally using the concept of the borrow, but you have to indicate that there is a final borrow. Okay, so when you calculate 29 minus 54, you will get a final borrow. Is this clear?
Yes.
Yeah.
Okay, this is expected because the result, if you calculate 29 minus 54, the result will be negative 25. So far, we don't know how to represent negative 25. I will talk about it later, how we can use the 2's complement to represent negative 25. But if you do it using the concept of the borrow, you will get a borrow. The final borrow will indicate that the result is negative. Right. So now, back here. How can we do addition in hexadecimal? So what we have done is that we have done it in the case of binary. Let us do it. We can do it in octal. We can do it in hexadecimal. In fact, we can do it in any number system that you like. I'm going to show it to you in hexadecimal, but you can think about doing it also in other number systems. So let us take a look here at these two numbers. Now, each digit in hexadecimal is how many bits in binary? So this 5 here is how many bits in binary?
4, I think.
4.
4 bits, exactly. Each digit in hexadecimal, because it is hexadecimal, is radix 16. So each one of these digits is 4 bits in binary. Now, how many bits exist in these two numbers?
16, I think.
No, we have actually 8 digits, right?
8.
And
Yeah.
8 multiplied by 4 is equal to what?
32.
So these are 32-bit numbers. I'm showing them as 8 digits in hexadecimal, but these numbers are 32 bits in binary. I can convert them to binary. I can do the addition in binary, but I would like to do it in hexadecimal. Okay, but these numbers actually are large. Okay, so these are 32-bit numbers. Type. Let us start by adding 5 plus b. What is actually 5 plus b? What is b?
11.
11.
16.
Okay, so what is 11 plus 5?
16.
16.
How do
So
I
F,
represent 16 in hexadecimal?
F.
F as F.
No,
No, it
F
is
is
15.
15.
Oh, yeah, you can. So 0 and
1.
And 1.
yeah,
And the
and
carry.
1. Yeah.
So in this example, you can see that 5 plus b, which is 5 plus 11 equal to 16. So here the sum, if it is greater than or equal to 16, because we cannot represent 16 as a digit. So if it's greater than or equal to 16, so what you have to do is that you have to subtract. You can say minus 16. You get 0 as the digit, and you get the carry is equal to 1. So here we have 0 as the sum, and the carry here, which is shown on top, this is my carry, is equal to 16. That's my carry, 16. Now, notice that the carry in binary is 2. The carry in decimal is 10, and the carry in hexadecimal is 16, because the radix is 16. You understand this?
Yeah.
So the meaning of the carry changes from one number system to another. So in hexadecimal, the carry, which is shown as 1, is 16. Okay?
Yes,
Let
but
us
we will add
continue.
it normally. 1 plus 6 plus 4, we will add it normally. 1 plus 6
Yes,
plus
add them normally. Yes. What is 1 plus 6 plus 4?
B.
B.
11, which is B. Yes, just write B. There is no carry. Because we did not reach 16 or over, so there is no carry. So if it does not exceed 15, there is no carry. How about 8 plus 8?
0 and carry
0 and carry 1.
Exactly, 0 and the carry. Because we have reached 16. So we say 16 minus 16 is 0 and there is a carry. Now, how about 1 plus 2 plus E?
1 and carry 1.
1
It is actually 1 plus 2 is a 3. E is 14. So we get 17. So therefore, 17 minus 16, we get the sum is equal to 1 and there is a carry. Continue.
D.
Yes. Continue.
B. C.
C, which is equal to 12. Continue.
F.
Yes. Continue.
A.
Exactly. Is there a final carry here?
No.
No, there isn't.
There is no carry here. So actually, final carry is 0. Okay. So basically, there is no final carry, so it is 0. Okay. So in this example, we did not really get the final carry, but sometimes you might actually get the final carry. That might happen. It means that here in this case, in this example, my sum is exactly 32 bits, but sometimes it might exceed 32 bits. It might actually become 33 bits. We get a carry. Ahmad, you have a question?
Yes, can we add decimal with hexadecimal?
Anna, let me ask you this question. Should you do something like this? Can you add decimal with hexadecimal?
I don't think.
Why?
Change first.
Because maybe because the radix is different.
Yes, because the radix is different. So you answered yourself. Okay.
Yes.
So how do you actually do something like this?
Maybe I should convert it to hexadecimal or
converted,
decimal.
yes, converted. So either convert the decimal to hexadecimal and add them in hexadecimal, or convert the hexadecimal to decimal and add them in decimal. So you should not really mix. Okay, is this clear?
Yes,
all right.
yes, clear.
All right. Let us talk about how we can do subtraction in hexadecimal. Okay. So how do I subtract 5 minus b?
We need to borrow.
We need to borrow. What is the borrow in hexadecimal?
16.
16.
Exactly. So what is 16 plus 5?
21.
21.
21 minus b. What is minus 11?
Minus 11 is
10.
10.
Or A.
What is 10? What is 10 in hexadecimal?
A.
A.
Exactly. Exactly. So therefore here you can see that 5 is less than b. So the difference is negative. So we have to borrow. So when we borrow, the borrow is 16. So 16 plus 5 is 21 minus the 11 is 10. So therefore we write A because digit 10 is A in hexadecimal. And we put the borrow. The borrow is appears here. Now I'm putting minus 1 just to remember that you have to subtract it from the 6. So now when you subtract, so you get 6 minus the 1, you get 5. 5 minus the 4, you get 1. That's easy. Okay, so we borrowed this 1 from the 6. Okay, it became 5. And then the 5 minus the 4, it became 1. So let us continue. 8 minus 8 equal to what? This is easy.
0.
Now here, you tell me.
We need to borrow.
Yes, so the borrow is what?
16.
So it becomes 18.
18.
Plus 2.
18 minus the E.
4.
4 and borrow.
Exactly. Exactly. So you understand how this is done. You see, we are doing the arithmetic in hexadecimal now. 7 minus, so we borrow from 7 becomes 6. 6 minus 5 is 1. This is easy. Let us continue.
16 plus 19 minus 9. 10. Or A.
Exactly.
A and borrow.
A and the borrow.
Borrow.
Okay. So now when you borrow from the C, what does it become?
Well,
B.
B, which is 11 minus 3.
What do you get?
8.
Okay, 9 minus 1.
8 also. 8 without borrow.
So we have done it. We have done it. We have done the subtraction. Now notice that there is no final borrow, but sometimes you might actually get a borrow here. If you get the borrow here, this will happen if the first number is smaller than the second one. You might actually get a borrow, and that's an indication that the result is negative. Okay. But here, we did not get the borrow. So if you look at the first number, it is larger than the second one. So we did not really get a borrow. But sometimes you might actually get a borrow. Right. Let us take a look at multiplication. I would like to show you how we can do multiplication in binary. Is it difficult to do multiplication in binary or easy? Do you know how to do multiplication in decimal?
Yes.
Easy.
Yeah.
Well, in the case of decimal, you had to deal with 10 decimal digits from 0 to 9. You have to memorize a multiplication table. That was difficult, right? Do you like the multiplication table, or did you forget about the multiplication table?
Also, I memorized it. So.
Okay, good. If you want to do arithmetic, you have to memorize these things. In the case of binary, it's very, very simple because we only have 2 digits, 0 and 1. So when you multiply anything by 0, it's equal to 0. And when you multiply anything by 1, x multiplied by 1 equal to x. That's it. So you see that binary multiplication is a lot easier. It's a lot easier than the decimal multiplication. Okay. So now what we have to do is that we have 2 numbers. The first one is called the multiplicand. The second one is called the multiplier. So what I have to do, I have to take each bit of the multiplier and multiply it by the multiplicand. So we start with this one here. So when I multiply this one by the 1100, I'm going to get 1100. But then when I take the 0 and multiply it by the 1100, I'm going to get 0000. Here I have 1 multiplied by 1100, I'm going to get the 1100. Very easy. But remember that these bits have weights. So what you have to do is that you have to shift these partial products. And then you can actually add them. So first we get the 1100. When I multiply this one by the 1100, you just can copy it here. That's it. Very easy. When you multiply this 0 by 1100, you just get zeros. Very easy. Now you multiply the 1 by 1100, you replicate it here. But notice that how I'm shifting. So basically here there is a 0. Here I have a 0 and here I have a 0. You don't really have to write them, but you can if you want to. But make sure that you shift. Because shifting is essential in the case of multiplication. And you are shifting because actually these bits are at different positions. And finally, we also have this one multiplied by 1100. We get the 1100 also here. Now, what do I need to do?
Addition.
What should I do next?
Addition.
I just have to add, exactly. Just add them in binary. We already know how to add numbers in binary. Let us do them. Let us do it. So when you add, this is what you will get. So basically, you drop the 0 here. 0 plus 0 becomes 0. 1 plus 0 plus 0 is equal to the 1. 1 plus 3 0 is equal to the 1. 0 plus 1, this is easy. 1 plus 1, 0, and there is a carry. So let us put a carry here. 1 plus 1 is equal to 0, and there is a carry. So let's put a carry here. And this is actually my final carry. So this is my final product. Now, take a look at these 2 numbers. Let me clean up this slide. So notice that the first number is 12. The second number is 13. And we got the product equal to this number. If you convert it actually from binary to decimal, you will get 156, which is 12 multiplied by 13. If you multiply them, you will get 156 also in decimal. So it works. That's basically how binary multiplication works. So it is done using, it's very easy. You multiply 0 by the multiplicand, you get 0. You multiply 1 by the multiplicand, you get the multiplicand. If you have n bits multiplied by n bits, you get 2n, the number of bits in the product. So here we are multiplying 4 bits by 4 bits. So the product should consist of 8 bits. That's the product, because we are multiplying 4 bits by 4 bits. So always the product is double the number of bits in the multiplicand. So because here we have the multiplicand is 4 bits and the multiplier is 4 bits, so the product will have 8 bits.
If it is 5
this
bits,
is done using shifting and addition. That's it. This is how we do binary multiplication. It's easy. It's not that difficult. You need to practice this. Ziad, you have a question?
Yes, doctor. If the two binary numbers is not the same number of digits, for example, one is 5 digits and the other is 4 digits, should we?
Okay. One way to do it. Okay. So if you have 5 bits multiplied by 4 bits, the product will be 5 plus 4 equal to 9 bits. All right. So therefore, if you have the numbers don't really have an equal number of bits, you know that the product, if you have, for example, n bits multiplied by m bits, so you have 2 different number of bits, m and n. So you know, we can prove it mathematically that the number of bits in the product will be m plus n, the number of bits in the multiplicand plus the number of bits in the multiplier. This can represent exactly the product. All right. But usually when you are dealing with computer hardware, both the multiplicand and the multiplier are typically, they actually have the same number of bits. So we have seen addition, multiplication. We have seen addition, subtraction. We have done it in binary. Also, we have seen how to do it in hexadecimal. We can also do it in octal or any number system. Okay, once we understand basically how it works, then in fact, we can do it in any number system. Also, we have seen multiplication. Let me talk about shifting the bits. Now, what happens if the bits are shifted to the left by 1 bit position? This is a question to you. What happens if I shift the bits to the left by 1 bit?
We multiplied
yes,
by 2.
Abdul Malik?
We multiplied by 2.
Exactly. We multiplied by 2. So I have here an example about this. So suppose that we have here 8 bits. So the number here is 5. 5 is 101 in binary. But if I shift it to the left, it becomes 1010, which is 10 in binary. So you can see that the number was multiplied by 2. So notice what when we shift to the left, we insert a 0 here. It becomes the least significant bit. That's what will happen when we shift the bits here to the left. Okay, so notice that how we have shifted is 0. Okay, so this becomes the least significant bit, and the number now becomes 1010, which is 10. So we have multiplied the number by 2. Now, in the case of decimal, when we shift the digits to the left and we insert a 0 at the end, then this is multiplication by 10. In the case of binary, when we shift the bits to the left and we insert a 0, then it becomes multiplication by 2. If I would like to do it in hexadecimal, and I would like to shift the digits to the left and insert a 0 at the end, what will happen?
Multiply by 16.
16.
Exactly. And then octal?
By 8.
Multiply by 8.
Exactly. So now you understand it, okay? Right. How about, let us go back to binary, okay? If I shift by 2 bits to the left, what will happen?
2 by 4.
2, so 4.
Exactly, by 2 squared, by 4. So this is multiplication by 2. So suppose that we repeat it, okay, we take the 5 and we shifted 2 bits to the left, then it becomes 20, okay, multiplication by 4, by 2 squared. And if I shifted by 3 bits, it will be multiplication by 8, 2 cubed, 2 to the power 3. So notice that, okay, if we shift the bits to the left by n bits, then this will be multiplication by 2 to the power n. This is the meaning of shifting the bits to the left. We are multiplying. Okay, so as long as we have sufficient space to store the bits, then if we shift by n bits, then this will be multiplication by 2 to the power n. Remember when I talked last time about multiplication? So what we were doing is that we were shifting and we're adding. That's how multiplication is done. So we're shifting to the left, and we are actually adding the partial products, and then we accumulate we sum all these partial products to get the final product at the end. So this is the meaning of shifting. Okay. In the case of decimal, if I shift by 2 digits to the left, it will be multiplication by, and I insert 0, 0 at the end, it will be multiplication by what?
By 10.
10 squared.
10 squared, which is 100. Exactly. So we are multiplying by 100. If I shift by 3 digits to the left and insert 0, 0, 0, it will be multiplication by
10 to the power 3.
Exactly. So you see, it's the same rule. It's the same rule which is applied to any radix r. Okay. Right. How about if I do it, okay, with shifting to the right? Okay, so let us actually shift the bits to the right. So what will happen if I shift the bits to the right by 1 bit position?
Divide by 2.
Divide by 2.
Exactly, division by 2. Now there is a bit which is shifted out, and this bit which is shifted out becomes the remainder. So let us take a look at the same example. No, another example. Suppose I start here, for example, with 38. Okay, so this is the representation of 38. It is 1, 0, 0, and then we have 1, 1, 0. If you convert it actually from binary to decimal, you will get 38. Now, if I would like to shift these bits to the right, then the number becomes 1, 0, 0, 1, 1, and this 0 is shifted out. This is the remainder. And this number becomes 19. So we are dividing by 2. Now, let us continue shifting to the right. Let us take the number here, which is 19, okay, and shift it to the right again. Or take the number 38 and shift it to the right by 2-bit positions. Okay, so if we shift to the right by 2-bit positions, I'm going to get, okay, the 1 and the 0, these 2 bits will be shifted out. And 1, 0 is actually 2 in binary. Okay, so the remainder will be 2. And the number will be 1, 0, 0, 1. Okay, so let me just highlight. So let me just, okay, use my pen tool. I have to use my pen. Okay, so you can see that so these bits actually are shifted to the right. These bits here are shifted out. Of course, the least significant bits here are zeros. So when we shift to the right, we insert zeros here from the left. And these bits are shifted out, and this is the remainder. So the least significant 2 bits are now the remainder. In this example, we get the remainder equal to 2. Now we get the result equal to 9. So if you multiply 9 by 4, you get 36 plus 2 will give you 38. Okay, so this is division by 4, and you get the remainder, which are the bits which are shifted out. You understand this? So if I would like to design now a divider in the hardware, what I really need to do is that I need to shift to the right. In the case of the multiplier, we shift it to the left. In the case of the division, I have to shift to the right. So this is really the basic idea for division, if I would like to divide in binary. Notice that if I would like to divide, if I would like to shift to the right by n bits, if I shift to the right, it has to be to the right. And it has to be by n bits. Then in this case, we are dividing, it will be division by 2 to the power n. And the remainder, which is r, this will be the bits that are shifted out. You understand this? Is this clear?
Yes.
Yes.
But what if,
You have any question about this?
yeah, Doctor,
Oh.
in multiplication, what if the bits get shifted out on the left? Like
that would be a problem. Then you start actually losing bits. Okay, so what you need to do in the case of multiplication, you have to increase the number of bits that you are storing. Yani, for example, remember in the case of multiplication, when we multiplied 4 bits by 4 bits, to avoid the losing the bits, the product was 8 bits. So we increase the number of bits
yes.
and the result. Okay, Abdul Malik?
Yes, clear.
Right. Any other question? All right. So this was my last slide. This is about binary arithmetic. We are going to revisit, okay, binary arithmetic later when I talk about circuits, and we'll see how we can design circuits that can actually do the arithmetic inside the computer system. So we are going to design an ALU, an arithmetic and logic unit. We'll see. We'll talk more about it later.